Now this one, also the same horseshoe magnet on the balance pen. Now they give us north and south. Then we can know for sure. Oh, got magnetic field lines and they're all pointing this way from north to south, outside of the magnet. Okay lah, I just draw two enough already lah. You get the idea. Current, we don't know. We'll see. Maybe we'll be asked to find the direction of current later. Anyway, the wire is clamped at ends A and B. It's because you don't want the wire to be flying around. You want the magnet to push down on the balance. Okay, when a direct current is switched on in the wire, the reading on the balance is seen to decrease. State and explain the direction of the force acting on the wire. Wow, how to do Firstly, state and explain. When you see this thing, you should already ask yourself, what kind of answer should I write? What are you trying to state and explain? The direction of something. So state, you are answering the question, what? What's the direction of the force? What? Explain is why. Why did you say the direction is like that? So you must state and explain. They didn't really give us the direction of current though. But they did tell us that once you turn on the current, the reading of the balance decrease. That is a very important clue. So let's see how to brain this. Once you turn on, the balance reading decrease. In other words, reading decrease. You can say that it implies that the magnet become so-called lighter to the balance. Balance like, why the magnet suddenly so light? So the reading decrease. So the magnet become lighter. Means there is a kind of force that is pulling the magnet up. Like this. So this will be the force on magnet by wire. The wire is pulling the magnet up. Oh, so it becomes lighter. Okay, but here they're asking about what? Read very carefully. The force acting on the wire. On the wire. So because of Newton's third law, if you have a force pulling the magnet up, means the magnet must also be pulling the wire down. Like what we looked at in the theory video earlier. So this is the equal opposite magnetic force. And this is one that we want to explain and talk about in this first part of the question. Okay, so save that down somewhere. Let's see how we can write this for 3 marks. Wow, very interesting. 3 marks! Force acting on the wire, state downwards, why downwards? So you kind of have to explain. So what you could say here is that the force on wire is downwards. Why Well, how we know it's downwards? Why not upwards or something like that? So you can say force on wire is downwards. So force on magnet is upwards. And this causes a decrease in reading. Decrease in balance reading. Because the magnet appears to have become lighter. Magic. Someone else is lifting it up. Okay, so force on wire is downwards, therefore force on magnet is upwards, and that causes a decrease in balance reading. But you need to say how these two are linked together. Why one down, 1 point up? That's because of Newton's third law. Okay, so you can say because both forces, how are they related? Are equal in magnitude and opposite in direction. Trying to write fast, guys. Have patience. Opposite in direction. If you have a way to shorten this answer, sure. But these are the main points you want to hit. Newton's third law. 3 marks. First one, if you mention force on wire is downwards, that's 1 mark. And you say force on magnet is upwards. And how do you know that? Because current reading in the balance decrease already. The magnet become lighter. But not actually. The mass is still the same. It's just another force is lifting it up. And you mentioned also Newton's third law. Both forces equal magnitude, opposite in direction, Newton's third law. Okay, this will be the final mark. B1 mark, thankfully. So if you get any of these points, you can already award it to yourself. Okay, Now, we also have to do one more thing. State and explain the direction of current in the wire. Wow. Current in the wire. So you must say, what is the direction? Okay, what and why do you say that? How you know? So we go and look at the diagram again. Okay, need to find the direction of current now. So I'm going to rub off this extra force to clear up the space a bit. So this FB that I draw is the force on wire. On the wire. Something is pulling the wire down. Now how to use your hand now? First thing, B is pointing there. Force is down. Remind yourself a bit what your fingers stand for again. So B is going to be pointing upwards, your thumb. If your forefinger is pointing in a certain direction, there must be current. Oh, this thing is backwards. Let me change this diagram. B is the other way. Oh, this current is backwards. So let me delete this. You know, different setups can work too, but to not confuse ourselves, this one is B. Current is this way. Thumb will be force this way. Didn't check the diagram earlier when I pasted it in. Never mind. Okay, so this is Fleming left hand rule. So when you want to adjust, make sure your pointing finger is aligned with the magnetic field. So you're pointing kind of to the top right. Like that. Pointing up there. Then you have a force downward. So make sure your thumb is pointed down. Then your middle finger, you have to check where it's pointing. If you find very hard to imagine this is 3D diagram, then like what we saw in the theory video, you can always have the option to redraw this whole horseshoe magnet into something easier to brain, such as this, north to south. Oh, so magnetic field is pointing towards the right. Force downwards. Wrong color pula. Force downwards. Okay, now this one should be easier to do with your hands. You point your pointing finger to the right. Make sure your thumb is pointing down. So to the right and down. Your middle finger, if you align your hand with the screen, your middle finger should be pointing into the screen. Here, let me zoom in a bit more so you can see. Okay, so your pointing forefinger, point to the right, thumb down, middle finger into the screen. So I'm going to draw into the screen. Shall we draw an X here? Wow, what happened to my thing? There we go, X. X means current into the page. There. So if you want to redraw into the 3D diagram, means current will be flowing this way into the page. Okay, so that is current. Now you need to tell the question, how you know current is that way and what is the direction of the current. So let's see. Current will be flowing from where? From B to A, right? So it flow from B all the way to A. So we want to describe that in our answer. Okay, if you find like, wow, I don't know how to use my hand, rewind a bit and double check. Make sure to check with someone until you can get this one right, how to use your hand properly. Left hand, huh? Do you know which is left hand, which is right hand? Please tell me you know which is left and right. If not, this chapter will be quite the big brain time for you. Okay, current in the wire. How do you know it's pointing from B to A? You say, using Fleming's left hand rule. Oh, need to explain how to use Fleming's left hand rule. No need. You just say, using Fleming's left hand rule, current is flowing from is. There we go. Is from where? Just now we say direction, right? Don't say into the page because the original diagram doesn't have into or out of the page. Say current flows from B to A. B to A. We redraw on the right, only become like that. Okay, so current is from B to A. 2 marks for this. It's a M1 A1 combo. So if you say Fleming left hand rule, M1, from B to A, A1. If you just simply say current flow from B to A, you might not get it if you didn't mention Fleming left hand rule. So remember, you want to find what you call this force, current, and things like that. Left hand rule. Left hand rule, okay? Now we go on to the final part of this example video. Now this part is a little new because this question, we haven't really learned the chapter yet at this point in time. But don't worry, We will learn it anyway. So why not, since we are here? So a direct current of 4.6 amp caused the wire to change by that much. Cause the reading to change by that much. So we know that if you have an I of this, then you will have some kind of change in mg. Change in the balance reading of that much. Okay, but now a direct current is replaced by an alternating frequency, 40 Hertz, and an r.m.s of 4.6. Oh my goodness. This is a preview of an AC chapter, a very short alternating current chapter, but they like to throw this kind of question everywhere. So, okay lah, might as well we just do it also. Alright, so how do you brain this? On the axis, sketch a graph to show a change in balance reading over time of 50 milliseconds. So until the end of time lah. So what does the alternating current do to the balance reading? First, my question is, what does the current do to a balance reading in the first place? So here, if you have a steady, this is what we usually say, a steady DC. DC is direct current. So if you have a steady direct current flowing through, you will have a steady constant force pointing down, which is the FB over there. What happens if you have an AC current? Wow, what is AC current look like? Come, I show you. So you have DC current, which will just be like that lor. If this is what, 4.6 amps current against time, then it'll just be 4.6 amps all the way. No changing problem. No changing business. So during this whole time, there will be a force acting on the wire. But if you have an AC, AC means the current will change direction and will change magnitude as well. So you could have something like this. Zoom, 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 zoom. Woo! Alternating current. This is direct current. Interesting. So how do we find the force? Okay, let's slow down. If you can figure out how to draw this, we can figure out how to understand this better. So let's pause a bit and think, okay, what's the equation now? We have seen earlier that you can kind of relate the change in the mass reading with BL over G times I. If you're wondering where this comes from, go check out the theory video from before, or go check out your notes. We looked at how this thing can be derived, how the change in mass is related to the current through the wire. But that was in DC. Now if this is AC, that means this thing is oscillating up and down. Which is this one lah, oscillating up and down. Everything else is pretty much constant lah. Length is constant, G is constant, B is constant. So that means now the mass reading will also be oscillating up and down. Sometimes it goes a big force, sometimes a small force, sometimes a very big force, sometimes a very small force. So that is how we can think of how to draw an oscillating graph. That's the first hint. It should be like a sine graph or cosine, either one of it. But it'll be oscillating. So let's assume it's a sine graph. Okay, so what will be the magnitude of this graph? What is the period, frequency, magnitude? Let's go through step by step and see how we can figure this out. So one important tip is when they say AC of frequency 40 Hertz, that means they're referring to this graph. Frequency 40 Hertz, which means the period will be, remember how to calculate this, F equals to 1 over T. So T equals to 1 over F. And this will give you a value of 25 milliseconds. So that means one full cycle will be 25 milliseconds. So you check marker. This graph, until 50, so about 25 somewhere here, you should complete one cycle. Okay, that's the first hint. That's the important one. 3 marks here, right? Probably one of it is talking about period. Second one, what's the amplitude of this M graph? How to find? What's the maximum current it can have? If we can find maximum current, we can find the maximum delta M. This one, we'll need to use the r.m.s to help us out. Because they told us that they have the root mean square of the current, 4.6 amp. What is root mean square? It's just a way to calculate kind of like the root mean square 4.6, is it? What was it? 4.6 amps, okay. So don't worry about where this equation comes from too much. We'll learn more about it. But at the moment, you can calculate with this equation, r.m.s equals to the amplitude over square root of 2. So the amplitude here will be square root of 2 times 4.6 amps, which will give us 6.505 ampere. That means at times, you will reach about 6.5 amps. Very big. Then you will be 6.5 amps, but in a different direction. Also very big. Negative lah, okay? Negative means in the opposite direction. So it is at these points where you have the largest force. Here also largest force, but in different direction. Largest force. Okay. So now we know our period. So we know current oscillate, the change in mass or whatever your current balance is reading will also oscillate. So, how to find the maximum change in balance reading? Oh, this is in newtons. My bad, didn't see that earlier. So this will be mg instead. Okay. So how to find the largest force? Okay, we're going to use some calculation now. We know largest force occurs there, largest force occurs there. We need to know the amplitude of at least one of them. So step is step 2, I guess. Step 3. Wow, what is happening to my colors? Haywire. Step 1, step 2, step 3. Okay, step 3. So the largest force will be BIL. So you need to calculate BI maximum L. So what will be this one be? Oh, you can do some ratios based on what they give you, or you could calculate from scratch. What I mean by ratio is that they give us a very important hint. This one. Why did they tell us this? When you have a current 4.6, means you have a force of this. Oh. I and F is related, right? So we can say force is proportional to I. No matter which force, which I you are at. Okay? So then you can say force over I, do a ratio, force over I. And they told us in the question that if you have a 4.6 ampere flowing through the wire, then you will experience 4.5 times 10 negative 3 Newton. But now I want maximum force, right? And I know at the maximum force, this will be the current. So 6.5. So I write there 6.5 ampere. What is the force? Find the force. We would get a value of about 6.358, 359, somewhere there lah. 3589, I don't know. Let's just put it at 6.36, somewhere there. Oh, times 10 to the negative 3. Forgot about that. Millinewton. Alright. So this is the maximum possible force that can be experienced or measured by this balance reading. And that occurs when your current is maximum, force is maximum, and we just found that with some ratios. Because lazy to calculate again. You can also calculate lah, up to you. But a bit long. You have to find BL constant. Okay, so 6.4, we're going to say, alright, so we know, number 1, balance reading will be oscillating. There should be 2 cycles, 1, 2. And we know that the maximum force that can be measured is about 6.4 times 10 to the negative 3. 6.4 is where? Somewhere here. So might as well add a dotted line to make sure we don't draw out of here. So this will be positive 6.4 mn in one direction. Then when the current change direction again, the force also change direction. So the balance reading will be a negative value down here. Wow, this question is okay, we are there. Now lastly, one full cycle should stop halfway at 25 milliseconds because we said that that's one full period of oscillation, alternating frequency ma. Okay, now we draw the graph now. Okay, let's do this. So I'm going to try my best to draw a nice graph. Should cut off something like that. You know, if you want to make it look nicer, you can divide out halfway, pass through here. Something like that. Oh man, this looks very curvy. You get the idea, sinusoidal curve. This is how you can draw one like that. So there's 3 marks for this. First mark comes if you know there are 2 cycles. 1 cycle, 2 cycle. That is the first B1 mark. Second mark, did you know that 1 full period is 25 milliseconds? Do you cross there? If you did, T, to find T, then that is B1. The last mark is, as you may have guessed, the longest part that we took to find. If you knew the amplitude of this change in balance reading is 6.4, that's a final B1 mark. So student may ask during exam, Miss, not enough time to do all this. How to do all this? Well, that's because we are not used to doing this thing. But over time, when you are more familiar with the AC chapter and as well as magnetic field, then you don't have to show all this working. You can write less, but still be able to sketch this graph. Okay, so I'm showing all this so that you can see step by step my thought process, how I decide what to do and how to interpret this information. Okay, so don't worry, we'll have a whole chapter just on AC, where current is alternating up, going down, up and down, and up and down. So the force will also go up and down, up and down, up and down, up and down. And yep, that is what we call alternating current. So that's this question. And these two are kind of like the basic horseshoe magnet kind of setup. So in the next few examples that you will see, the single question ones, those will look at more unusual setups. No, setups that have twisty wires, got torque, and all kinds of other experiments. But those are fun. So I'll see you in those next few examples. If not, see you in the next theory section.